Hi everyone, welcome to the final session of the CV workshop series. I'll be presenting the session on revision. Okay, about me. I'm currently in my third year of CS at UFT. I took a gap year last year to work at Amazon. That was my ASIP co-op term, and I'm currently researching inverse rendering at a group at UFT called TCIG, and my main interests are in computer vision and graphics. And if you have any interest in these topics, feel free to come and talk to me afterwards. So what is 3D vision? As a whole, it basically is how can we make sense using computers or algorithms? How can we make sense of multiple images taken of some scene or an object? And you can see from the slide here, whenever we have multiple images of a scene, right? All the images, they capture the same object from new angles. And we can make sense of these new objects using some basic math. We can learn from these pictures how objects are supposed to look like. And we can make real world decisions from just pixels on the screen. And yeah, these are like some of the applications of 3D vision. So the most obvious one that I can think of the head is autonomous cars. This is what autonomous cars see. Especially, it's very prevalent in the Tesla autopilot system, where you can see what the car thinks is around it on that iPad screen. And like in this case, it's able to figure out that there's a car next to it, there's a bunch of cars next to it, and with really high precision as well. And obviously with this, it can make decisions on where to drive, how to take turns, so on and so forth. And this is like a very great use case of 3D vision, where it has multiple cameras on the car, and using these multiple cameras, it runs some inference to generate the 3D scene on the road. Another use case is video games. So gaming is mostly about graphics, not specifically 3D vision, but a lot of the principles from vision apply to graphics as well. So this is obviously in-game, right? But it looks so nice. It looks like crystal clear. There's so many reflections going on. It's almost as if the person took a video of a car in real life, but it's all being rendered from a program on your computer. And the principles of vision are camera geometry, how to light objects in a scene, how to build the meshes in a scene, how do we represent them in software, and how can we make them run efficiently on a desktop computer. Yeah. AR is also another really interesting use case. I found this video online of a person doing this on the, let me mute it, of a person doing this with the Apple Vision Pro. I think the Apple Vision Pro is like a very advanced use case of 3D vision, where they have like a bunch of cameras on the VR headset, and the cameras, they build this 3D map of the scene that the person's in. And with the 3D map, the Vision Pro goggles are able to track the person's hand and position in 3D space. And with that, they can essentially do this. They can draw in 3D, and the whole system knows where a particular stroke was drawn, at like what angle and whatnot. And yeah, like I think that's just amazing. Okay, so this is the agenda for the meeting. We'll talk about some background, and then we'll go into the various advancements in the field. Okay. So when we talk about 3D vision, we want to talk about 3D objects, right? And how can we like store them and think about them? So there are two main domains in this: explicit representations and implicit representations. So to think about explicit representations, think of this, the object on screen. So it's a wireframe mesh of Woody, and the whole object is stored as a list of polygons, essentially. So you can see like the squares on the wireframe mesh. That's basically one instance of the mesh, and it's all like stored as a list in memory. And it's called explicit just because I can explicitly locate a point of the object by just indexing into it. Or I can like think of a point with some mathematical equation. And to think about implicit, you can think of it like as a set of points, or like the set of the object is defined with some mathematical formula where I'm not able to figure out a point of the object, but the set encapsulates what the object is supposed to look like. So if you think of that square there, it's basically saying all the points in blue, they are blue because their function evaluates to less than 0, and all the points in red are red because their function evaluates to more than 0. So if I represent my set in this format, I allow to evaluate my scene at each of these locations to figure out what the object looks like. In this case, it's a bunny, and the bunny looks like a bunny because all the points which are red have some value corresponding to the SDF and some value which is more than 0. So I have a quick demo on Desmos. Okay, so this is a sphere, right? You all know how a sphere looks like. And I can think of a sphere using this function up here. So f of uv gives me these 3 coordinates, and I can evaluate them for this domain, and that'll give me a sphere. And this is an explicit representation of a sphere because I can input any 2 numbers, like a and b here, and I can get a point on the sphere. So I know exactly where each point on the sphere is given 2 input values. Now, I can also represent a sphere with this equation, x squared plus y squared plus z squared equals to 0. Basically, it's saying that every point, x, y, z, which has a distance of 1 from the origin. And this also is a sphere, right? But how would I query a point from this? I can't really. Like, I have to try multiple values of x, y, z to figure out if a point lies on the surface. And the way Desmos does this is that I'm pretty sure it does some conversion internally to show a sphere, but to draw a sphere just like that, it's not trivial, right? Like, you can't figure out what a point is. And that's the whole intuition between implicit and explicit. Okay, and then a quick intro into neural networks. A neural network is basically just a function, and it's a function composed of multiple interconnected layers. And these layers learn from input data, and they learn to model what the input data is trying to represent. And a specific kind of neural network is the MLP. And basically, yeah, it just maps inputs to outputs through multiple layers of transformation. The core idea is that we have a bunch of these nodes internally, and each node just does that math, like that math formula, xi, y, wi plus b, a basic multiplication plus addition. And this math formula can be expressed as a matrix multiplication. So all the values in one layer can be stored as a matrix. So that matrix times the input matrix is the output of one layer. Yeah, and like in terms of math, that's how it's represented. After every multiplication, there is another function that's applied on top of them, which is called the activation function. And this activation function is non-linear. And what that means is that it's not just composed of like some basic product plus addition. And this non-linearity is what helps the model to learn complex data sets, etc. Okay, so we have our MLP, which is f of x, which is just composed of this long chain of layers. How can we train this? We define an objective, and the objective is defined by a loss function. So let's say our model outputs some y value, and we know the ground truth value of what you want the model to learn, y hat, and we can take some difference of these two values to define a loss. So now we know how much our model is correct or wrong based on our loss function, and we can update our model using the chain rule essentially. So if we differentiate our loss with respect to the model parameters, we can calculate the gradient. The gradient is basically just the derivative of the function in terms of multiple variables. And we can update our model parameters W and B with the gradient. So at a very high level, I'm basically just doing differentiation on the loss. And with that, I can calculate what's known as the gradient, dl over dw. And then with that, I can update my model parameters. And that's how the model learns. Okay, so camera fundamentals. A camera basically maps a point in 3D to a point on a 2D plane. And throughout this entire talk, we'll think of the camera as a pinhole camera. So I'm sure y'all have used a pinhole camera before, right? Or have you? No? Okay. Have you guys ever seen like a picture formed on the back of a screen when light enters through the curtains of your room? No? Okay. If you look in the morning, if your room faces the sun, and I mean the window faces the sun as the sun rises, you'll be able to see like the picture of the outside world on the back of your screen, I mean the wall, because you can think of your curtains as a pinhole, and when light rays enter the pinhole, they enter in that fashion, as in like a ray from the top of the tree could enter the pinhole and then land here, from the middle goes to the middle of the screen, and then from the bottom goes to the top of the screen. And we use a pinhole because each point in 3D can now be mapped to a point on the image plane. And this gives you a very concrete understanding of how a scene is supposed to look like. And like most cameras also function under this pinhole assumption. In reality, it's a bit more complex, but for the math purposes, this should be good enough for us. Yeah, so a point in 3D maps to a point in 2D, right? And if you think of the pinhole as this point here, a point in 3D lands all the way there. So if a point has XYZ coordinates in 3D, we can do some basic math with similar triangles and get the point on 2D on the image plane. And like that's your whole transformation essentially. So the further an object is from the screen, the smaller it appears. And this follows from the basic math, it's just multiplication. Now, if we have points along the same ray, they all get mapped to the same point on 3D, I mean on the 2D plane, right? So if you have a bunch of objects stacked in front of each other and you take a picture of them, obviously you can't see the object in, like that's in the back, but you know from basic geometry that it would also map to the same point on the image plane. And because of this, we define coordinates known as homogeneous coordinates, where we just add an extra 1 at the end of them to show that some coordinate xy comma 1 is the same as the same coordinate scaled by a scalar factor. Yeah. So now we can just define our 3D projection as a matrix multiplication formulation. So I have a point in 3D, and if I multiply that point with my matrix P, I can get that point on my image plane X. And this gives me a very nice way to represent this transformation, right? Like with matrices, it's quite simple. And like I mentioned before, because of this homogeneous formulation, it's all just defined up to scale, where any point along some ray, it'll map to the same point on the plane. So this equation holds for any scalar multiple of P of X, P times X. And P essentially can be defined with the camera parameters. So from the previous slide, it depends on the focal length and the distance, right? So those values can be encoded into P in this fashion to form a matrix K. And one more thing to note is that we have different coordinate systems for the camera and the world. So the world can be defined in one coordinate system and the camera is in a different coordinate system. So we just need a way to translate between the world and the camera coordinates. And that can be defined by rotation and a translation. So this gives me another set of parameters to define this world to camera translation. And putting it all together gives me my P matrix. And that's how you can define mathematically how coordinates in 3D map to coordinates in 2D on your image plane. I won't go into the details of how this works entirely. It's just good to think of it as just a matrix multiplication. So P times big X gives me my small x on my image plane. Okay. Also, feel free to ask any questions if you guys don't understand what's happening so far. Structure for motion. So this is the main, the main application of 3D vision, or like the basis of how most of the advancements in the field are made. So to motivate this, I'll show you this video. It's a video of a drone, and the drone is autonomously moving in the space. And it's able to do this by constructing this mesh of points of the room that it's in, and it's able to detect like where these, I guess, points are, and it knows not to hit like the wall or the desk object there, and the drone is able to navigate by itself. And the user has defined like some flight path for it, and it's able to fly without like hitting anything. And like that's one application. And the drone just has a camera that's mounted onto it, so it's able to see like this view here, and it's able to figure out points in the scene, and there are 3D locations in scene as well, so it knows not to hit those points. So more concretely, the goal of structure for motion is, given your input images, like from multiple angles, in the case of the drone, it has multiple input images because it flies around the scene. Can we figure out some amount of 3D points in the scene, and as well as the camera intrinsics and camera poses? So if you recall K, R, and T from the previous slides, and we want these points X sub J to be consistent across all the views, right? Because once these points are consistent across all views, then the drone can make concrete decisions on how to move in the scene, how to navigate the scene and not hit anything. So we have our camera model where it defines a transformation from 3D onto 2D, and we want to figure out some amount of points in 3D and as well as the camera poses. So the camera poses against the R and T values as well as the camera intrinsics like the focal length and the other values as well. In terms of math, it comes out to this equation where we have these many knowns and unknowns. So using basically an alg, we want like 2nm number of equations, because each matched point from two images gives me two values. There's not much to go deep into this. It's just something to think about. If you want to figure out those many number of 3D points, we need this many number of pictures. So I'll talk about this in terms of two views. So if you have two views of a scene, some object, we'll capture the same object from different angles, right? So it'll form roughly the same image, but it'll be shifted or transposed or like angled by some difference. So let's say I have a point P1 on my image, and that point P1 corresponds to some other point on my second image. This relation is defined by a line. So I can shoot a ray from my camera 1 origin into 3D, and you can see that this ray maps to a line in camera 2. So my corresponding point P2 in camera 2 can lie anywhere on this line. And using this information, I can create these two equations. So that E times P1 gives me my line equation, and multiplying that line with P2 will solve the line equation. So E is just a matrix for now. It is called the essential matrix, and it defines this relation of a point in one camera to a line in the second camera. And this is like a bit more general explanation where I have my point P, and that point P corresponds to point P1 in my first camera, and joining that point P with my origin gives me a line in 3D. This line in 3D maps to a line in 2D on my second camera plane. That line is called the epipolar line, and the corresponding point P2, it has to lie on that same line, and like because of the math that we defined in the previous slide. Yeah. So we have a way to relate correspondences of pictures across two camera views. But so far, this is just defined in terms of camera coordinates. Like I mentioned before, we have camera coordinates, and we also have pixel coordinates, which are actual pixels on your screen, right? So to do this conversion from pixels to camera, we define one more matrix called the fundamental matrix. And it's just defined by this transformation. I won't go much into it, but this is what we want to solve for. So if I have two pictures, I want to learn this matrix so that I can learn the correspondence between points from one camera plane to a different camera plane. And the way we solve for this matrix F, the fundamental matrix, is we have our input of points. So I have matched points across multiple camera images. And I'll ask a question. How do you guys think we get these matched image points across multiple images? Like if I have an image of a bottle from this angle and like a different angle, how can I match like a point on the cap across these two pictures? If you guys have attended the previous lecture, like the previous workshops, it should make sense. No? Okay. You can use like an object detector, like a basic CNN could work. There's also like some more classical methods where you can like analyze the picture for templates. Like a cap has some shape, right? So you can match for a shape across multiple images and then you find these image matching points. Okay, so we have these matched points across scenes and we want to learn the fundamental matrix. The fundamental matrix has these properties. It's a 3x3 matrix. It has a rank of 2 and it follows the epipolar line constraint where a point in one's image plane maps to a line in the second image plane. And if my correspondence lies on that line, the line equation evaluates to 0. So for each correspondence, we can get this big equation. Again, not too much to dive deep into. It's just saying that from each point, I have two values, x, y, and x hat, y hat, and we get this equation. And for solving it, we can formulate the previous equation into a matrix, and we have 8 unknowns, right? Because our matrix, the fundamental matrix, is a 3 by 3 matrix, but it's actually 9 values. So we say only 8 correspondences because we have 1 value that's left up to scale. And the scale factor comes from our homogeneous definition of all coordinates. Again, not too much to dive deep into. If you have any questions about it, you can ask me later. And we can solve for our fundamental matrix with the SVD. So the SVD just says that any matrix A can be recomposed into 3 individual matrices. And the properties of the SVD help us to solve for equations of this format, where I want to learn what's the matrix F, and if it's defined by this constraint, A times F, where I want to minimize what F is, I can solve it using the SVD. So I get F from the SVD, and then I can recompose F to give like my 3 by 3 matrix, the fundamental 3 by 3 matrix. Okay, so we know what F is, right? But what about the actual value P? If I have F to define how points translate across planes, how can I find my actual point in 3D? Because like that's what we want to solve for, right? For the drone to solve for, and for anything like cars or whatnot. With the fundamental matrix F, we can solve for the camera matrices, P and P prime, and that's again from just a singular, like a basic math equation. And we can solve for the point in 3D using a process called triangulation. And that's basically saying that given my 2 points, x and x prime, I can solve for an equation where the p times x and p prime, x prime both come from the same point in 3D. So with that constraint, I can solve for my point in 3D. So great. From 2 images, I have some math, which is just a bunch of matrix multiplications. I can solve for points in 3D. But obviously, my drone has multiple images, and it moves across the scene, right? So with multiple images, I get new angles of my object, and new angles give me more data, so more points, and it's also better for the drone to fly around in the scene. So how can we adapt my initial algorithm to do this for multiple views? And it comes very naturally to do it in a sequential manner, where I run my one algorithm on like the first 2 pictures, and then for each additional view, I can run the same algorithm with the previous pictures that have the same known points in 3D, and I can recompute the new fundamental matrices, the new camera poses, etc., etc. And this happens in a sequential manner. So for each new picture, I do the same process, learn new points, and improve my point set of the scene. And we have one last step called bundle adjustment. And that's basically is, can we learn to minimize the error across all of my learned parameters so far? So after some number of iterations, I do this optimization step where I project all my points in 3D onto my points in 2D. And I know where my points in 2D are because I detected them with my object detector. And it's again just doing a basic camera projection. So we learned K, R, and T. So once I do this, I can calculate where the parameters think a point is and where I found out a point is, xij. And with this, I get some error value, and I can and the algorithm will learn to minimize this, to minimize the error from all the learned parameters across all scenes. So now we have like a software algorithm where I can take multiple images of a scene and get points in 3D, right? So this is one paper that was published almost 10 to 12 years ago, I think. And it's called Building Rome in a Day. And basically what they did was they took a bunch of pictures of the Colosseum from Google. And obviously the Colosseum is a very well-known structure, right? So there's a bunch of pictures online. But all these pictures are not calibrated. They're randomly taken from random angles. So how do we construct a 3D mesh of these of the object from these multiple pictures? And essentially they ran the same algorithm as before, and they get this high quality point cloud of the Colosseum, and you can see where the cameras are. So there's cameras all across the ground from multiple angles, all pointing up, and it's really high quality, like the point cloud mesh. And to think that this was done almost 12 years ago is still mind-blowing, and it's still a very highly useful algorithm used in so many applications. So we have obviously robotics, the drones, one example, for geospatial mapping, for surveying, and also visual effects. And the visual effects is one that's quite interesting to me. And this is one application of that. So if you've ever seen high-speed car chases in movies, you can almost guarantee that that car is not a real car. It's a fake car where they have this a buggy of sorts, and they put a visual effects model on top of that to put a car in the scene. And the way they implement this is that they have these trackers on the buggy, and these are your matched points across frames. So they track for these points across frames, and with that they learn the location of them in 3D. So once they know that location, they can insert a 3D model of the car that they want to insert, and it's quite quick and easy. So the fundamentals of what they're doing here is the same as structure from motion, where they track across frames, they build the structure, and then they insert the visual effects car on top of it. And I think it's quite interesting how such a simple math algorithm is used in big budget movies as well. And that buggy is called the Blackbird car. It's used in car commercials, in movies. Yeah. Any questions so far? All right, moving on. So the previous algorithm, it gives me a bunch of points in 3D with multiple images, right? So it's quite good for applications in robotics where I know where a point is in 3D, so I don't want to go and hit that point. And it's useful for understanding the geometry of a scene. But let me go back here to the room. But basically, I get an output that looks like this. It's just a bunch of points. So it's not pretty, right? It's just points in 3D. There's no color for each point. There's no actual explicit mesh for each point. It's just a point. So can we do something better than that? So the next topic, neural variance fields, it solves a problem called novel view synthesis, where given input images, can I generate a new view of the same scene? So this technique, it's able to learn the color of the scene, the appearance, the lighting, as well as the geometry. And one very popular example of it was used in the movie Superman. So this movie uses a technique called Gaussian splatting that I'll talk about later on, but it also solves the same problem of novel view synthesis. So if you guys recall this one scene in the movie where they play a message from his dead parents, I'll just go back. That scene was rendered using the Gaussian splatting technique. And the way they solved it basically is, let me skip forward, they have this section of a bunch of cameras in a globe, and the actor does their performance inside the center of this structure, and the cameras record like the performance from multiple angles. So this gives us like various views, various lighting conditions of the same actor, and with that, the person or like whoever's making the movie can construct a new angle of the same performance so that it can help them get like a different direction of the movie, a better angle, maybe even try it with like different lighting effects. Yeah, so you can see they're able to move around this scene of just like one performance. And yeah, they're able to go around, they're able to, does it show? Oh. Yeah, they're able to add like many effects, do all sorts of VFX techniques, just because they use this technique of Gaussian splatting. Yeah, and that's one application of novel view synthesis, where you have a bunch of input pictures. Can I generate a new novel view from a new angle of the same scene? Yeah. And like one, I guess, caveat is that this is happening for a stream of pictures, right? Like it's in 4D essentially. So you have your pixels, I mean your space in 3D and like a time dimension, so that's a 4D. But I'll just be talking about static scenes, so just like static pictures of one scene. Okay, so again, more concretely, given a set of views of an object, we want to learn novel views of the same object. And that's what NERF and splatting try to solve. The main theory behind NERF is to learn my scene as a function. And this function is called a radiance field. So if I learn a function, I can evaluate my function at new inputs, and with new inputs I get new views, and like that's the whole theory behind using it as a function. Okay, so radiance fields, like I mentioned, are continuous functions, and if we define our scene as a function, we can't store all points explicitly. So going back to the circle example, I showed the circle in two different formats, right? So the explicit way and the implicit way. In the implicit way, it was just a function x squared plus y squared plus z squared equals to 1. And that's a function. That's what, in our case, we also want to learn some function. But it's also a continuous function, but it's implicit. And we make it implicit because it's very easy to represent scenes with an implicit function in this way. So our function f takes in a 3D coordinate x and some direction d, and we learn the color from that location. So if I input a point in 3D and some direction, my function will give me a color if I viewed my scene at that point. And we show theta as the parameters that we want to learn for our radiance field. And we also want the function to be differentiable, because if we can show it as a network, I can apply my same techniques that I know how to train a network to the same problem here, and I can just train it with like machine learning. So going back to neural networks, we just define our function as an MLP. So a bunch of matrix multiplication layers, activation layers, and the output is the color again, and another value, which is the density. So how dense should a color value be at that point in 3D and at that direction. So one more thing that that's on the slide is the encoded position, right? I'll talk about this in the next slides, but again, the main inputs are just a point in 3D, so x, and the direction, and the function outputs a color and a sigma value. So the encoded position, we use something called positional encodings in MLP networks, and the reason we use them is, I'll talk about this with this example. So what's happening here is this is simple MLP, and the MLP is trying to learn the picture of the fox. So that's fox, and it learned, like the MLP on the right learned the fox quite quickly, whereas the MLP on the left learned it, like it just learns the high level features of the fox. And the one on the right uses the positional encoding technique, the one on the left does not. So you can see that MLPs, they have this bias towards like large scale features, like the overall shape of the fox, maybe some color, like the gray color here and the brown color there, but it's not able to learn like small details like the eyes, the fur, the nose. And this simple trick of a positional encoding trick, it's able to fix this and make the MLP learn the fox picture like quite quickly. So what I'm actually showing you here is the value of the output of the MLP as it trains across multiple epochs. And you can see that it learned the fox quite quickly with the positional encoding, whereas the one without, like, it struggles even at the end, like it's not able to learn. And you can see in terms of graphs as well, where the one, like the MLP with the encoding has a lower error. Where is that? The one without the encoding has a lower error, and the one with has higher. The metric on the left is just showing how close my outputted picture is to the actual picture. So higher means better here. So ML models have an inductive bias where they tend to learn high scale features first, and they struggle to learn low scale features, like in the case of the fox, the fur, the eyes, the nose. And that's why we use positional encodings in MLPs. A quick, example of inductive bias is this. So let's say I have a data set of these points here. They form some curve, right? Now, if I want my function to learn this curve, I'd want my function to also be a curvy function. But if I just use a linear function like ax times ax plus b, and my parameters are a and b, the function will fit to a straight line, and it tries to minimize the error as best as it can. But it can only learn a straight line because that's the bias the function has. So that's a way of thinking in terms of MLPs as well. And MLPs themselves are also functions, right? And they also have a bias towards data of large scale features. And we use this one trick, the positional encoding, to ignore this and learn features quicker and faster. In terms of math, it's just a bunch of sines and cosines of my input coordinates with multiples of pi's inside them as well. And so if I have an input, the positional encoding of the input is defined by this. And it basically represents one point in 3D in terms of the Fourier decomposition of a wave at that point. And this helps the model differentiate multiple inputs and learn features quicker. All right, so now I defined a function with this architecture, and the function gives me a color at each point in 3D and some direction. how can I form a picture with this function? We use a technique called volume rendering for this. So the way our function learns a scene is by learning essentially a cloud of colors in 3D. So if I have a cloud of, let's say, this triangle object in 3D, I mean, in this case, it's 2D, of this triangle object, I can generate a picture of this triangle and the square by shooting rays into 3D and evaluating the function at each of these points. So at all of the circle points, I evaluate the function and they give me some color. And with that color value, I can superimpose the colors back onto the ray and then they land back onto my pixel and that'll give me an image. And that's just the high scale understanding of volume rendering. In a more math sense, you have a ray from the camera and you plug in your function outputs, your color and sigma at the points on the ray, and then you integrate them with this math equation to get your final color of a pixel. Again, I won't go much into this. It's just to give an intuition of how you weight the colors with your density, and it's just like a multiplication of these two values across a ray to get your final value of a pixel. And then in practice, it's done in a discrete fashion because you can't sample infinite number of points. You sample a set number of points along a ray, you evaluate the function, do the same product, color times the alpha value, and you get your final color of your pixel of that ray. And since this process is just a bunch of multiplications and additions, it's fully differentiable. Okay, so the whole pipeline is just that. We shoot a ray from a pixel, evaluate the function along that ray, add those color values up, and we get a final picture. In terms of learning the radiance field, it's the same as learning a network. I have my ground truth, IK, which is my input pictures, and I have the valued from the function I cap k, and we just take the pixel-wise loss of the two pictures, and with this I can optimize my MLP. So while it's training, it looks something like this. In the picture here, it's trying to learn the 2D scene of a triangle and a square. So initially, you can see here that it shoots out a bunch of rays. It evaluates the function at all those points along a ray, and it forms this blobby purplish mesh initially. And that's the MLP bias that I talked about before, where initially it learns the large scale structure, some color as well, but it's not quite fine grained. And across iterations, it figures out some more features, and towards the end, it's able to learn the triangle and the square and where they are exactly, in this case in 2D. Yeah, and in 3D, it looks something like this, where again, you have multiple views, the same formulation where you shoot a ray, evaluate points along that ray, and form your picture. With your picture, you can calculate the loss with your ground truth and train your function. And this whole process is differentiable. And we like differentiable functions because we can train them with MLPs. Okay. So play. Yeah. And these are some results with nerves. So you can see how the function is able to learn this smooth representation of a scene. And there's very little inconsistencies across the scene. The color is preserved, the geometry is preserved. There's some amount of reflection as well in the glass in the back that's preserved. And this is quite groundbreaking in terms of novel view synthesis. With just some pictures and a small MLP, we can learn novel views. And it was quite groundbreaking, like when it came out 5 years ago in the paper. Yeah. So you might be wondering, why do we go through this whole process of volume rendering and making a function learn a scene implicitly, and not do what graphics has done all along? Doesn't that look so beautiful? Well, so why don't we do that? Any takers? Oh, okay, that's one answer, correct? Not correct, but it's a answer. Okay, so the reason we don't do ray tracing or like regular graphics rendering is because the process of rendering in the traditional graphics way is not differentiable. So going back to the idea of implicit versus explicit, graphics uses an explicit representation of a scene. So game developers, they define their objects, in this case a circle, and they define light sources in the scene and like colors of the circle, their reflectance values, etc., to define how my scene is supposed to look like when I render it with the camera, like in the program. And the way a picture is rendered with ray casting is the camera shoots a ray into the scene. The ray intersects some object in the scene, and then from there it calculates the light or the color at that point with a recursive ray shooting algorithm. And this works great for graphics because game devs can explicitly define scenes and their objects and make them look just perfect. And it works quite well on even the hardware. The bad thing for us is that this ray casting technique is not differentiable. So if I want my function to learn a 3D mesh in this type of format, it's quite hard to learn it, and there's no like actual way of learning a 3D mesh in this format, and that's why we can't use ray casting. Now, why volume rendering, you might ask? Because it's smooth, because it's differentiable. The function is just one function, and it's continuously learned in terms of software. It's just a bunch of matrices and additions, and this helps to learn like the smooth nature of novel views across the scene. So that's why it's used. Some limitations of NERF is that this volume rendering approach does not model light very accurately. It's able to learn color and some amount of reflection across shiny objects, but not true reflections. So there was one paper that was published after the original NERF paper where they tried to improve upon reflections. So the regular NERF has like something like this where it's quite blurry in terms of reflections, and they added some more techniques to get it a bit better. But even then, it's not as good as the ground truth where it's very sharp and defined. So that's one major limitation. And another limitation is that NERF is quite slow in itself because the scene is implicit, right? And to render a scene, we have to evaluate the function at multiple points in the scene to figure out the color, and then like superimpose all those colors to get a final picture. So it's quite wasteful if my scene is like very empty. If I only have like one object in the scene and my camera is quite far, I have to evaluate all the points across the object and at the object to figure out the color of it. And that's why they made a new technique called Gaussian splatting. So why do we need Gaussian splatting if NERF has like such good results like this? I mean, it does look quite good, but why should we improve upon this? It does the same thing as NERF, but it's very, very, very fast, and That was the main advantage of Gaussian splatting when it first came out, and that's also why it's used in movies, like in the example that I showed before. It's quite quick, and it has the same quality, if not even better. And the key idea of splatting is we try to represent the color of the scene sparsely only where density is non-zero. So we don't want to store values where a value does not need to be stored. So if an object is there in 3D, I want to store only the color and location of that object and nothing around it, because that's not needed for me to learn. And that's the whole algorithm actually for Gaussian splatting. It's quite small if you think about it, but it's very intricate, and also quite innovative actually if you look a bit more deep into it. At a high level, we have multiple images, right, from multiple views, and we learn the structure from motion points from the previous slides. So I have matched points across images, and I have points in 3D learned from these pictures. Then at each of these SFM points, we initialize Gaussians. I'll talk about what Gaussians are later on, but think of it as like a blob around each of these points. So now I have a blob around each of these points and some color associated with these blobs. And this is very explicit in 3D, right? So the color can be superimposed onto a plane, and with this I can get a picture. And these blobs are updated iteratively with some optimization technique, and that's how the model learns a novel view. Okay, so a bit more concretely is, again, we have a bunch of input points, input images, and we calibrate them with SFM from the previous slides. SFM gives us a sparse point cloud, and I want to learn the radiance or the color and across multiple frames. So going back to what Gaussians are, a Gaussian is just defined by this fancy math formula, but it's just a way to define, in our case, like a blob in 3D, and the blob's like shape, length, and like width, also in 3D, and its mean location in 3D. So the mean is mu, the covariance value defines how much the blob stretches in each direction, and we also have an opacity value for each blob to store how bright or dim it should look like in my final picture. And we learn the color of these blobs using a technique called spherical harmonics. So why do we use Gaussians? Going back to the previous question of why do I have this explicit way of storing a scene? Why not just volume rendering? Or why not the mesh way of storing a scene? Like why Gaussians, right? Any takers? Again, think of it like we can store a Gaussian as a math formula. So why Gaussians? Yeah.
Similar to before with the ray tracing example, it's like the meshes are not differentiable.
Mm-hmm.
As long as you look at a certain set of points.
Yeah.
Compared to the parameters of the Gaussians.
Yeah, that's perfectly correct. So a Gaussian can be defined by this math formula, right? And it's just, again, a bunch of products and additions, and we have this exponential term here as well. Because they are differentiable. So since we define Gaussians as a math formula, we can learn these parameters using differentiation. And we love differentiation, again, because we can train networks with them quite easily. Now, a Gaussian in 3D can be shown as a Gaussian in 2D with a basic math translation. Yeah, I won't go again much into depth here. I'm just like the math here is just to show that we can represent the Gaussian in 3D and splat it back into 2D with just a bunch of multiplication and transformations. And the final line here shows that the mean of a Gaussian on 2D is defined by this, and the variance is defined by this. So at a high level, Gaussians in 3D map to Gaussians in 2D. And a Gaussian in 2D is just like an oval elliptical shape. Yeah. I talked about color with a technique called spherical harmonics. The color value is defined by, again, some fancy math, and it's dependent on the viewing direction. So a Gaussian from different angles looks different because the color is defined based on the viewing angle. Spherical harmonics comes from quantum physics, but we people in CS steal things from physics all the time and math for our use cases. Yeah, and that's the actual expanded value of the Y term from the previous slide. It is quite big, but there's no need to learn all this for our use case. We just evaluate this big term for a small set of values, and we store them in memory while we do our whole process. So that this fancy Y value, if evaluated at just like small m and l indices, it basically represents like a bunch of functions defined on spheres. So we store the first few indices of the harmonic, so 0, 1, 2, 3, and they look like this in 3D. So you can see here it takes in a theta value and a phi value. So that's how we represent angle in 3D. So for my polar and azimuthal angles in 3D. And for each angle, the function represents some scalar output. And for different values of m and l, this is what the table looks like. To give you a more intuitive understanding of harmonics, I found this video while I was doom scrolling of this person trying to represent the earth actually with harmonics. So there are a bunch of harmonics and there's a scalar value for each of them. If we add these all up with some scalar value, they learn the structure of the earth on a sphere. And as we increase the number of bases of the harmonics, the earth's structure gets more refined and it's more sharp. Yeah, this is just to build like the intuition of how we can use harmonics to learn the view dependence of color. In this case, the person built the earth. Yeah, I think it's quite interesting the way he did it. Okay. So how do we render the Gaussians? In NERF, we sampled points along a ray in my volume of cloud, and I learned the color. Oh, someone has a question here. And in Gaussians, we have these blobs also of Gaussians in 3D. How can I render my picture with that? The basic intuition is that you can just superimpose Gaussians because Gaussians map from 3D Gaussians to 2D Gaussians. And by superimposing them with color, you can just figure out what they're supposed to look like on a 2D image plane. And again, the formula for that is just this. Not the formula, the algorithm. I'll talk about it, but it's all, again, like quite small. So the authors describe a frustum. A frustum is just this cone-shaped volume from a point, and they evaluate all the Gaussians stored in that cone-shaped volume. And for all those Gaussians in that cone shape volume, we we splat them back into 2D. Once we splat them back into 2D, we can superimpose the Gaussians based on their depth in the scene. And based on the color, we can blend the Gaussians to give a final value for each pixel. And the good thing about doing this is that since all these Gaussians are stored as just explicit points in space, and the blending and this whole color thing is done with just like pure math, there's no need for a network. It's just storing some points and splatting them back into 2D. And that's the main advantage of Gaussian splatting, where it's really quick because there's no need to evaluate some network at each point on an array. We can just splat them because we know explicitly where they are in 3D. In terms of training, we say training, but it's not really like training a network. We're just training this model of Gaussians. We define like the loss based on the image loss. So like image-wise difference, and this DSSIM loss is another loss used for showing how close two pictures are. It's like a similarity loss. And like I mentioned, this whole process is differentiable because Gaussians are differentiable. We get the image with the differentiable process, like splatting them is differentiable, blending them is differentiable, and the final image that we get can be differentiated as well to learn the Gaussian values. So for this model, I say model in quotes, we want to learn these parameters. The means of the Gaussians, the scale of them, their rotation in 3D, the opacity, and the color of them. And I say spherical harmonic coefficients because we just store like the first few coefficients, and each coefficient has some coefficient, like a scalar value for each of them, and we add them up to get the color at some angle, right? So we want to learn these values per Gaussian for the scene. And these can be learned, right, from the loss that we have. But the input is just a bunch of sparse points. The output of the image would be also like a sparse image, I guess, like of just a bunch of Gaussians in 3D. So how can we get them to cover the entire 3D scene? We do this by this iterative approach of adaptive density control, where if a Gaussian is in a location and that location is quite sparse, we know it's sparse because of the gradient that we calculate with our loss. If it's quite sparse, we split the Gaussian into two and we re-optimize. If the Gaussian is in a very dense location, it over represents that point in 3D. So we split the Gaussian once more and the bigger Gaussian into two smaller Gaussians to again learn the scene. So this helps to add and remove Gaussians from the set of all Gaussians. And the way this branch is taken is with, again, checking with the gradient of the loss. So if the gradient of the loss is higher than some threshold, they run like this check of, do we split the Gaussians, make them smaller or bigger, and do we add or remove Gaussians? And in terms of results, it again gets really high quality results. So this is a scene of an indoor scene with a bunch of plants, and you can see it's able to capture like really high quality detail of the leaves, the vines hanging around, and you can even learn the reflection of the water. So you can see like the water reflects the roof of the structure, and it's physically accurate. Even the color is accurate, the lighting is accurate, and the person goes inside the scene, the water, and the way it represents reflections is that it just thinks that there's some object under the reflective surface, and that's how it renders reflections. And you can see by like when they go towards the edge of the scene, these spikes appear. These spikes are the Gaussians that we trained, right? Around the edges of the scene, they're more sparse. There's not much data around there, so there's not much Gaussians there as well. And those spikes, when superimposed, form your actual picture. One more result that I wanted to show is I found this online where someone made a splat of the school atrium in Sanford Fleming. I think it's quite interesting the way they made it. So this is also a Gaussian splat. And you can see like in this area of the pit, it's quite high quality. Like the structure is well defined, the lighting is good, there's not much artifacts, I guess. The people look a bit weird, and you can see the artifact showing up here, but back in the center, back in the center, like it's quite good. And if I go towards the edge of the scene, let me try and fly out. Oh, where am I? Can I? If I go towards the edges of the scene, it gets a bit less dense in terms of Gaussians, and the output looks quite bad. And the main reason this happens is because they were like the person might not have taken any pictures in this region. So when the model learns this region, it just tries to approximate with some basic understanding of the geometry. And like go out. Yeah, here you can see like quite big Gaussians here as well, like that blob there, and like for more finer details, the Gaussians are quite small as well. And that's how Gaussians are represented in 3D to get your image. Okay. So some limitations for splatting is we get those artifacts like I mentioned with unseen regions, and like large Gaussians might give like random popping effects. It's memory heavy compared with NERF. If you want high quality splats, you have to store a lot of Gaussians for sharp details. And you can only like render scenes in which you have moved your camera in those angles. Again, like with unseen regions, you get artifacts. And yeah, that brings me to the end of my talk. Any questions? Okay. Thank you so much for listening. I hope I've inspired y'all to go into vision and like make great things. Thank you.